Okay, here, this is chemistry alternatives to practicals. And for the IGCSE exams, for the purpose of today's class, we're going to be looking at number one, collecting and testing for gases. We'll be looking at separation techniques, volumetric analysis, salt-based titration, then qualitative analysis or salt analysis. We're going to be taking each of these items one after the other. The first item here is collecting and testing for gases. I'm going to focus for now on collecting gases. In the chemistry laboratory, there are various methods used for collecting gases. The first method is the upward delivery method. The second method is the downward delivery method. The third method is collection over water. And lastly, we have the gas syringe method. The upward delivery method is used to collect gases that are less dense than air. What happens is if you have whatever reaction you have made that produces any of these gases that are less dense than air, the gases are going to travel through this delivery tube upwards where they are collected in a vessel you want to use to collect the gas that is positioned above the delivery tube so that the delivery tube delivers upwardly into the container. Examples of those gases are hydrogen, nitrogen, carbon monoxide. These gases are so light that they are delivered upward. So if they move along this duct, they're going to be delivered upward in this manner. They're going to occupy the upper part in this manner. So what happens here is the gases, as they move up the tube, they get to displace air that was initially in the tube. They displace air particles initially in the tube, and these air particles are displaced downward. So an alternative way of calling this upward delivery method, we can also call it downward displacement of air. So it's also called downward displacement of air method. But to be safe, we just look at them as upward delivery, downward delivery. But when we're looking at displacement of air, this method is downward displacement of air. The second method we have here is the method called downward delivery. It is the exact opposite of the air upward delivery method. What happens here is that gases like ammonia, chlorine, and carbon dioxide that are heavier than air, these gases are going to drop to the floor downwards when you collect them from a reaction because of their density. They are denser than air, so they drop downwards. So the tube is going to be oriented downwards and the container for collecting them will be positioned this way. Now, if we look very well, just like the other one, when these gases empty in here, they're going to push air particles in this tube in this direction, upward. So this method is also called upward displacement of air. So this method is also called upward displacement of air method. We go into the third method, which is collection over water. A lot of times, gases in the laboratory are collected over water. Whatever it is that is the reaction produces gases such as carbon dioxide, hydrogen, and oxygen, and they are delivered over water. It means these gases can bubble through water without dissolving in the water. They have low ability to dissolve in water. So these gases do not easily dissolve in water. So you have your gas collected in a jar here after it has passed over water. Now, this structure we have here is a beehive, and we have a test tube above it, or a measuring cylinder as the case may be, and the gas is collected here. Now, often these gases, when they are collected, may have little particles of water, attached to them. And in the laboratory, if you want to dry a gas, sometimes in your question paper, you may have a situation where a gas is bubbled. After it is collected, it is bubbled through concentrated sulfuric acid. The essence of bubbling a gas after it is collected through concentrated sulfuric acid is to dry the gas, because sulfuric acid is an example of a drying agent, especially for drying gases. So gases are passed through or bubble through concentrated sulfuric acid to dry them. At one point, you would meet in the course of your exam, you're going to meet situations where gases are passed through sulfuric acid, and you may ask, why do we have to pass the gas through sulfuric acid? They pass through sulfuric acid to dry the gas. So this is one point we have to note by the side. Example of gases that are collected like this are carbon dioxide, hydrogen, and oxygen. Then lastly, we have the gas syringe method. This is a very simple and is the most common method in the laboratory for collecting gases. We use a gas syringe that looks like this. Now, this part of the gas syringe is connected to a tube that delivers the gas from the reaction. And it is used to collect, matter of fact, any kind of gas. And not just to collect any kind of gas. Another important point is that it is also used for measuring the volume of the gas you have collected, because it has calibrations of volume on it. So this is the most reliable way to collect and measure the volume of a gas. So these are the four methods of collecting gases in the laboratory: upward delivery, downward delivery, collection over water, and gas syringe. We move to the next item, which is testing for gases. The gases for your IGCSE exams, you're going to be looking at the tests are hydrogen, oxygen, ammonia, chlorine, carbon dioxide, nitrogen, and lastly, sulfur dioxide. So move one after the other. Let's look at hydrogen. Now you have an unknown gas. You don't know what the gas is, but you want to check, could this gas be hydrogen? You can only do one thing to test a gas if it is hydrogen. You hold a lead splint over the unknown gas. A lead splint is a piece of wood very much like this that is on fire. It's been lit, so it has flame on it. Now, if you hold it over the gas which you do not know, but you want to check if it is hydrogen, if this gas burns or the splint burns with a squeaky pop or an explosive sound, then that gas coming out is hydrogen. Else, it is not hydrogen. The next way to test, the next test we're going to have here is oxygen. In the case of oxygen, you do not hold a glowing splint, a lit splint. Instead, you hold a glowing splint. You must know the difference between a lit splint and a glowing splint. A lit splint has a flame, but a glowing splint is just the flame on it has been blown out, very much like the tip of a lit cigarette. When it's blown out, it's like amber red. For those of us who occasionally we have barbecue, like we eat out or we have picnic, you see that when you blow into the hot charcoal, it turns amber red and then bursts into fire. It's the same thing that happens here. The amber red color or that orange color of the charcoal is what we call a glow. That's the glow of the charcoal. So you hold a piece of wood like this that's glowing. It does not have a flame. It's just amber red, and you hold it over the unknown gas. Now, if the gas is oxygen, oxygen is going to cause this flame to burst into a flame. That is because oxygen supports combustion. It is because oxygen supports combustion. The splint here is acting like a fuel. So oxygen supports the combustion of a fuel, which is in this case the piece of wood. So when I have something in a box like this, it's a point you don't want to just throw away. So that's the test for oxygen. It bursts into a flame, else it is not oxygen. If it does any other thing that is outside of this, bursting into a flame, then that gas is in oxygen. Let's test for ammonia. Ammonia is a basic gas. It's an example in chemistry of a weak base. Another example is hydrazine, but ammonia is the common thing they would tell you in the exam or you'll come across in the exam. So ammonia and hydrazine are weak bases, and we know what bases can do. They turn litmus paper that is red to blue. So ammonia and hydrazine are examples of weak bases. Should you be asked to give examples of weak bases, ammonia is a weak base. Okay then, now to test if a gas is ammonia, all you need to do is to hold a damp red litmus paper. The key word here is that the litmus paper must be damp. Whenever you are carrying out a reaction and you're testing for gas using a litmus paper, that litmus paper must be dampened or must be moistened. You do that by holding it over running water. And the reason why that happens is it's because you want the gas to actually dissolve in the water to show its character, if it's an acid or a base. Now, the positive result here is that a red litmus paper that is dampened and held over the unknown gas will turn to blue because ammonia is basic. The equation of that reaction is ammonia react with water and it forms the ammonium ion, which is NH4 plus, and the hydroxide ion. This hydroxide ion is what makes it a base because this is the ion that every other base forms when they dissolve in water. And this is the ion that actually the ion that receives hydrogen ion from an acid to form water. So this is the equation for the reaction. It's another thing you want to note. Equation for the reaction where ammonia acts like a base. So if the test or the gas behaves any other way aside this, then it is not ammonia. Next up, we have test for chlorine. Chlorine is a very important gas, but then it is toxic. It is poisonous. You don't inhale chlorine, or you don't want to inhale chlorine. For these reasons, we carry out the experiment in a fumes cupboard. So fumes cupboard experiments that involve toxic gases are done in a fumes cupboard. For IGCSE, it's another safety precaution you have to take when you are carrying out an experiment and the gas made in that experiment is toxic or poisonous. You have to carry such an experiment out in a fumes cupboard. That said, if we have a test for chlorine, all you need to do is hold any color of damp litmus paper. Since it's a gas, you have to dampen the litmus paper still. Any color, be it red or blue, over the unknown gas. Now, chlorine has the ability of bleaching a red litmus paper to white or bleaching a blue litmus paper to white. So, the litmus paper becomes bleached. That is a positive test for chlorine. Else, the gas is not chlorine. We move to carbon dioxide. Carbon dioxide test is a very popular test from elementary school. All you need to do is to bubble the gas made through lime water. And I said lime water is a solution of calcium hydroxide in water. Calcium hydroxide is called slick lime. Sorry about my calcium hydroxide there. It's actually C. Calcium hydroxide is also called slake lime, and it's written as CaOH bracket 2. That's calcium hydroxide, also called slaked lime. Now, if you bubble the gas through a solution containing water and calcium hydroxide or slake lime, which we call lime water, the lime water will turn cloudy or milky if the gas is carbon dioxide. Here, the lime water turns cloudy or milky, else it is not carbon dioxide. And that happens because the lime water, which is primarily slake lime in water, and the slake lime is the active ingredient, reacts with carbon dioxide, and this forms calcium carbonate, which is limestone, and water. This equation is balanced. Forms calcium carbonate and limestone. This calcium carbonate is what is responsible for the cloudiness in the solution because it is insoluble solid. While this is aqueous, since it's a mixture with water, this is a gas as carbon dioxide, and this is a liquid as water. This insoluble solid here is what is responsible for the cloudiness because it is insoluble and it's white. It is limestone that is formed. We move on to the next test, which is test for nitrogen. Nitrogen is known to quench fire. Nitrogen is known to slow down oxidation. Matter of fact, many packaged food, especially those packaged food that contain oil, they are always stored or kept or packaged with nitrogen in order to reduce the oxidation of the food and reduce the rancidity you get after. So things like cheese balls, peanuts, and what have you, we have nitrogen gas pumped into their containers or into their sachet to slow down oxidation because nitrogen takes away oxygen so that a material is not able to get oxidized. So all you need to do is hold a lead splint, and that's the lead splint again, over the unknown gas. What happens is, if the gas is nitrogen, it quenches the fire. It extinguishes the splint. If it does any other thing, it is not nitrogen. So the positive result will be the splint is extinguished. Else, it is not nitrogen gas you have coming out. Then lastly, we have test for sulfur dioxide. Sulfur dioxide is notorious. It is known to cause acid rain. So SO2, which is sulfur dioxide, causes acid rain. It is an acidic oxide. Acidic oxide, we know from our study that they are oxides of non-metals that behave like acids in the sense that they are able to react with a base. So sulfur dioxide is an example of an acidic oxide. It is mostly produced in power stations where they burn fossil fuels. Now, if you're carrying out a test for sulfur dioxide, you have to bubble the gas through acidified aqueous solution of potassium permanganate. Potassium permanganate is a purple solution, or is a purple colored compound when you dissolve it in water. And the key word here is you must always state, in fact, most times in chemistry, when I see these reactions involving these things, they're always acidified. So you must always say acidified aqueous solution of either potassium permanganate and or potassium dichromate. Potassium permanganate is purple. Potassium dichromate in aqueous solution is orange in color. Now, the positive result, if the gas that is produced is sulfur dioxide, is that the color of the aqueous potassium permanganate will become colorless. And if you have used potassium dichromate aqueous solution acidified, the color will go from orange to green. The equation of the reactions that happen is the active part of the potassium permanganate in solution is the manganate ion. The manganate ion is KMnO4. It has a charge of -1. The active part of the chromate or dichromate or the potassium dichromate is the chromate ion, which is Cr2O7. It has a charge of -2 or an oxidation state of -2. What happens when the color of the manganese ion changes to colorless is because the oxygen is given away in that reaction. So we have just manganese with an oxidation state of +2. For the dichromate, the chromate ion loses its oxygen, and then we have just chromium left with an oxidation state of +3. I like to remember this with one of is it Maya song. She says 1 2 3 1 2 2 3 1 2 2 3. I don't know what that song is, but then I remember this equation with 1 2 2 3, and we can say that this color here is purple and this is colorless. The color here is orange and this is green. So this is the confirmatory test that the gas coming from this reaction is sulfur dioxide. You can use any of them to confirm the presence of sulfur dioxide as the gas emanating from that reaction. A second learning objective for chemistry alternative to practicals here is analyze or looking at separation techniques. Separation techniques, they are physical methods. These are physical separation methods for separating mixtures. And you know what mixtures are? Now, mixtures are substances that are not chemically combined. They are mixed together, but they are not bonding. When you have two or more substances mixed but not chemically bonded, you have a mixture. Examples of techniques used in chemistry laboratory, examples of those techniques used for separating mixtures or physical mixtures are dissolution, sieving, filtration, decantation, magnetic separation, the separating funnel method, simple distillation, fractional distillation, flotation, centrifugation, crystallization, and chromatography. All these methods are important, but you see these ones in yellow, they are the ones that IGCSE always ask about. The IGCSE exams, they're always asking about these ones in yellow, talking about filtration, separating phenol, simple distillation, fractional distillation, then crystallization and chromatography. The solution for separating mixture of both soluble and insoluble solids. You have one solid is soluble, the other one is insoluble, but then they are in a mixture. For example, table salt and sand can be in a mixture. Table salt is soluble in water, sand is not soluble in water. Sieving is for separating mixture of solids that have different sizes. Filtration is for separating an insoluble solid from its solution. Decantation is for separating a dense solid from its mixture with a liquid. And magnetic separation is for separating a mixture of magnetic material from non-magnetic material. Separating funnel will separate immiscible liquids. While simple distillation is not just separating, but it's used to obtain, the key word here, it is used to obtain solvent from a solution. And then we have fractional distillation that is used for separating a mixture. That's mixture. That's used to separate a mixture of liquids that are mixable. And then we have flotation for separating a mixture of solid with different densities. One will have to float when you put in water in the mixture, and one will just sink to the bottom. Centrifugation is for separating immiscible solids in a solvent. Crystallization is for obtaining, this is also not for just separating, but for obtaining soluble solids from a solution. So you see, it's like the opposite of simple distillation, where simple distillation is going after the solvent in a solution, Crystallization is going after the solute in a solution. Then lastly, we have chromatography, which is used for separating things like dyes and colors and pigments. We'll go straight to the first one. The solution, you have a mixture of solids. One is soluble in a solvent, the other one is not soluble. I just put in water or put in a solvent, and you see that the white ones are soluble and they have dissolved in the water. Then the orange ones that are not insoluble, I can easily filter them away. The criteria for purity here, when we talk of criteria for purity, we're looking at the property of the mixture that allows you to separate them. And the criteria for purity here is difference in solubility. Difference in solubility of the various substances that make up the mixture. You see the white one is soluble and the orange one is not soluble. Decantation is a method for separating a dense solid from its mixture with a liquid. Sometimes we sieve rice after boiling like this. Now what happens is the orange one is the dense solid in a mixture with a liquid, but because it's dense, it goes to the bottom as you tilt the liquid, and with the help of a glass rod just to hold steady, you actually decant, and the liquid will just trickle down like this. By so doing, you have actually separated the liquid from the dense solid. Next is sieving. This is very important because I think here I actually put, sieving is not, this is actually filtration and not sieving. That must have been a mistake. This is filtration. Sieving is different. When we look at filtration, let me quickly do the correction. Filtration, no, this is the exact opposite of, this is the exact opposite of sieving. Filtration is for separating a mix of insoluble solid that is in a solution. Now, what it looks like when you separate using filtration, you have a filter paper inside of a funnel. Now, this is your mix containing the insoluble solid in a solution. You pour it in this way, and when you pour it, what happens is the insoluble solid is held behind by the filter paper, and that is called the residue, while the solvent part that is able to pass through the filter paper is called the filtrate. By so doing, this solution has been separated into residue and filtrate. Then there's magnetic separation. Magnetic separation is where you have a mixture of magnetic and non-magnetic materials. You introduce a magnet. The magnets can pick up the magnetic ones and leave behind the non-magnetic ones. The criteria for purity in this case is difference in magnetic properties. But for filtration, it's still difference in solubility. After magnetic separation, we have separating funnel. This is what a separating funnel in the lab looks like. It is a glass container that has a nozzle like this, that has a tap also. You introduce your mixture here, and then these are immiscible substances or liquids. You discover that since they are immiscible, one of them is going to have a higher density than the other. So we allow it to stand. The one with the higher density will go down or will settle down. The liquid with the lower density will float above. And with the help of the tap, you can slowly tap off you can slowly tap off the liquid with the higher density like that, while leaving behind the liquid with the lower density. This criteria for purity is difference in density or difference in densities of the two liquids. Next up, simple distillation, very important point, is for obtaining a solvent from a solution. You have a setup like this. This is a flask or round bottom flask. You connect a delivery tube. Here we have a condenser that will condense any gas that comes out of this mixture or this solution. When you heat it up, as you heat it up, it begins to boil. The solvent part of this solution will leave the solution and go through the delivery tube where it is condensed. So you have a solution here, but you are able to collect the solvent here because the condenser actually turns the gaseous solvent into a liquid you can collect. By so doing, you are obtaining the solvent alone from the solution. And let us not forget that in a condenser, water comes in from the base and leaves from the top. I've always seen questions in IGCSE, they tell you, put an arrow to show where water goes into a condenser and where water leaves the condenser. A condenser turns gas or gases to liquids. That's what a condenser does. In this case, you're going to get the solvent, which was initially a gas due to the high temperature, but now the condenser would help you to separate it by turning it into a liquid. And the criteria for purity here is difference in boiling point, because the solvent and the solute will have different boiling points. No wonder the solute will be left behind while the solvent, which is our main aim, is collected. We have fractional distillation. It's for separating a mixture. This is a mixture. It's for separating a mixture of liquids that are mixing. These liquids are able to mix. You carry out the same setup like a simple distillation. The only obvious difference is that this has a fractionating column. The fractionating column is a column of glass beads that are kept at constant temperature, a particular temperature. So what happens here is when you heat up the two or more liquids using a Bunsen burner, due to the difference in their boiling point, all of them, first of all, because of the high temperature here, would vaporize. As they vaporize, they get to the fractionating chamber or the column. The temperature of the fractionating column is fixed. So the gas that has a boiling point higher than this temperature will escape. And that gas will come out of here, get condensed, and you have the gas. But those ones that their boiling points are higher than the temperature here would recondense back into the liquid. I repeat the explanation again. You have a fractionating column here. When you heat up the mixture, having two or more liquids that are mixable, due to their difference in boiling point, since all of them become vaporized, they get here. The one whose boiling point is less than the temperature here will vaporize and is collected here after condensing. The one with higher boiling point will recondense here and come back into this container here. So that's fractional distillation. The criteria for purity is difference in boiling points. Still, difference in boiling point. Then we have flotation. Flotation is a very simple method. All you need to know is that when you have a mixture of solids where one is able to float in a solvent and the other is not able to float in a solvent, just introduce the solvent like water. The ones that can float or that would float, and the other ones will sink to the bottom. The criteria of purity is difference in density, in your densities, and you can actually easily skim off or remove the ones that are floating, thereby separating this mixture. Centrifugation is a common method of separating blood into blood cells and its plasma in a hospital. The blood cells are denser. The blood plasma, which is the liquid part of the blood, is lighter. So that part stays above the test tube that you have loaded into the centrifuge. So you have a test tube. You're going to have your blood cells at the base, while your blood plasma will be above. The centrifuge actually spins the whole blood sample to a very high speed, and then the separation happens. We move on to crystallization, which is actually very, if not the most important method of separation for GCSE exams. You have a solution where you have a soluble solute in a solvent. In this solution, you just pour the whole mixture into an evaporating dish. You gently heat up the evaporating dish and you begin to see crystals of the solid. Now you allow the whole thing, the evaporating dish, to cool. More crystals will form because solubility decreases with decrease in temperature. So as it gets colder, the crystals appear more. Then you can now filter off what you have left of the solution. The whole crystals will collect as residue and the filtrate will go off into this beaker. The residue is what we want because that's the solid. All you need to do now is to rinse and dry the solid, rinse in water and dry in an oven. By so doing, we have separated this mixture into filtrate and the residue, which is the soluble solid you have. So it involves one method that we already looked at, which is the method of filtration. So filtration happens when you do crystallization. Filtration also is needed when you do crystallization. And the criteria for purity is difference in solubility. Now, when you have more than one type of solid with different solubility, you see that at a particular temperature here, a particular one will crystallize out. You filter it, collect the crystal, while the other one is crystallized later and filtered, and its crystals collected too. Chromatography is the last method we're looking at today. In chromatography, you want to separate dyes. A lot of colors and dyes and pigments have constituents that have different colors. We know in our elementary school that green is a mixture of, I think, blue and yellow. Orange is a mixture of red and yellow, and so on and so forth. So some dyes actually have constituents that have different colors. To separate this kind of dye or pigment or protein, as the case may be, we need a chromatographic paper. A chromatographic paper is like a filter paper, though bigger. Now, with the use of a pencil, you draw a line on the chromatographic paper. You draw a line. That line, we call it a datum or origin line. And we use a pencil to draw the line. The reason why I use a pencil to draw the line is because if you use a pen is also an ink. It will also be separated. It's going to mess up the whole chromatography the aim of your carrying out chromatography. So then with a dropper, you add this drop of dye or ink on that datum or that origin line. This line is called origin, and it is drawn with a pencil. Now, you now carry the chromatographic paper now and immerse it or lower it into a solvent. That solvent level must be below the origin line you have drawn. You don't want your ink dissolving in the solvent or like the water or ethanol. It depends, and that solvent must be what? A solvent where the ink is soluble in. You don't use just any solvent. That ink must be soluble in the solvent. Now, you make sure the line or the origin line is above the solvent and you give it some time. If you give it some time, you see over time, the chromatographic paper will be absorbing the solvent up the paper. It will absorb it up the paper, and as it absorbs it, this ink now will separate into the various colors that it has. So this paper now that we bring out with the separated ink is no more called a chromatographic paper, but it is called a chromatogram. It is called a chromatogram now, no more a chromatographic paper. So a chromatogram is a chromatographic paper that now has the separated colors or ink. Now it is this paper that is now red, and we now see that ink has been separated. That is where your separation ends. But for the purpose of your exam, we go a little further to calculate something we call retardation factor, RF value. The retardation factor is given by the formula distance that an ink travels all upon the distance that the solvent itself travels. Now, if you look at this diagram, you see that this is where the solvent actually stopped after the experiment. That level is called the solvent front. Now, anywhere the ink stops finally is called the ink front. Let's say this ink actually travels from this origin, the blue ink, to a distance of 1.5 centimeters after the experiment. Red travels a distance of 4 centimeters, measured from the center of the ink to the origin line. Green travels 6 centimeters and 7 centimeters for yellow ink. The retardation factor tells us which is most soluble in this solvent. The retardation factor tells us which ink is most soluble. The higher the value of retardation factor, the more soluble the ink. The lower the retardation factor, the less soluble the ink. Now, if we're calculating retardation factor, let's say the distance traveled by the solvent itself from the solvent front to the origin is 10 centimeters like this. Then we can calculate retardation factor for the yellow ink or the yellow constituent of your dye or your ink. It is distance traveled by the ink, which is 7, upon the distance traveled by the solvent, which is 10. This will give us 0.7. Centimeters will cancel centimeters, so it has no unit. If we do the same thing for the green color, distance traveled by green from the origin is 6 centimeters, while the distance traveled by the solvent is 10 centimeters, we're going to have 6 over 10, which is 0.6. For red, it will be 4 over 10, which is 0.4. And for the blue color, it will be 1.5 upon 10. What is 1.5 upon 10? I don't know. I need to check my calculator. 1.5 divided by 10 is 0.15. 0.15. So these are the retardation factors. From these, we can easily tell that the most soluble is yellow. It means yellow is most soluble. Yellow is the most soluble. The most soluble way in that solvent, in this solvent. Now, it is not every time that the separation displays colors. For example, when we're separating proteins like pepsin, erepsin, and how do you call them in biology, they are all colorless. So should you do their chromatography, it may not have colors, even though the separation has happened, it may not have colors that you can see. That is why we use what we call a locating agent. We spray on the chromatogram. A locating agent like ninhydrin will expose the colors for us to see. It allows us to see the colors that otherwise we were not able to see in the chromatogram. Chromatography is used in drug testing. It is used in forensics and crime detection. It is used in pharmaceutical industries to actually test the quality or the purity or to maintain purity of drugs. It is also used by food monitoring and chemical monitoring agencies to know the safety of food and drugs and chemicals so that we don't have impurities and contaminants that are able to cause harm to us. This brings us to the end of separation technique. Next on our agenda is volumetric analysis, acid-base titration. This is a very interesting topic in aspect of alternative to practicals. Basically, what happens in titration at this level or acid-base titration is neutralization, which is the reaction between an acid and a base to form a salt and water. We all know what neutralization is. Now, if you doing a titration, we want to actually find out concentration of either the acid or the base, or we want to find out the volume of an acid that neutralizes a given volume of the base. So basically, it's like chemical stoichiometry. We want to look at quantities of either acid or base that actually interacted with themselves to form salt and water. What we do is we have, let's say, the base in a beaker like this. We have the acid in a volumetric flask like this. We have a burette. It's actually calibrated usually to 50 centimeters cube or 50 milliliters, which is the same thing. And we have a pipette, which always often has just a single mark on it. It's used for collecting definite volume of a liquid, definite volume. Burette has a tap, so it can be used to measure changing volumes of liquid, while a pipette measures only a definite volume of liquid. I'm going to write that down. Burette measures changing volume of liquid, while pipette measures definite of liquid. They all have their uses in a chemistry laboratory. What we do, I'm going to put this in a box too so that we know it's a point to differentiate between the use of a burette and the use of a pipette. Now here we are. For the purpose of this explanation, we're going to have our acid using a funnel poured into the burette that is locked. Next, we pour it such that it gets to the 0 mark on the burette, which tells you it is filled up. Next, for the base, we use a pipette, and we are able to use a pipette filler to collect a definite volume of the base. In the laboratory, common volumes of the base or capacity of the burette, they are usually 20 or 25 cm3, the most common burettes that are used. So you now take the volume of that of the base and pour that definite volume of base you've collected in a conical flask. Then you add an indicator in drops. Then you add an indicator in drops. Let me see if I can actually do a little more explanation on that. No, I can't. Okay, I can. Now that's your indicator. What I said here was once you have collected your base, you would now add some indicator in drops to your base. Now you have your base in here, collected with a pipette. The indicator will have a particular color in the base. Then you now transfer that here and do a titration by running the acid you have in the burette into it. So basically, you're going to take this out of here and transfer it here after you've taken or added your indicator, and then you monitor the color change as acid drops into it. You wait until when the color of that indicator for neutralization is exactly achieved, you stop your titration, and you now look at the volume of acid you have expelled that has been collected. Now, you're going to do a table like this, or draw a table like this. In the table of records, you have burette reading, just the final reading, the initial reading put on that so that I can easily do a subtraction and get the volume of acid I have used. You start with a rough titer, you get a first, a second, and a third. Now, some examples of calculations you have to pay mind to in titration are N equals CV and CAVA over CBVB equals NA over NB. N is number of moles, C is concentration, V is volume. It means number of moles of acid, Na, is equal to CV of acid, concentration of acid times volume of acid. Number of moles of base, Nb, is equal to concentration of base, Cb, and volume of base. We can divide them like you have in this equation. Now, this page actually helps us to see the procedure in carrying out a titration. Now, I have my base in here. I have explained this before, I'm explaining it again. This is my base. With the aid of a pipette, I'm going to take my pipette and collect a given volume of base. When I collect the given volume of base, which is like 20 or 25 based upon how my experiment goes, I'll drop it here. So my base has been collected and dropped here, all of it, in the conical flask. Then I'm done with the pipette for now. Next, I'm going to take up my indicator and I'm going to add drops of indicator to the base. I add some of this indicator to the base. There's going to be a color change. And having done it, I now take this and put right under here for the titration. Already, my acid has been put in this burette filled to the 0 mark. This is the burette. The acid has been filled to the 0 mark, full capacity, waiting to empty into the base. Now, remember the base has a color. For example, if I use methyl orange, the base would already be yellow. The base would already be yellow. Now, with the aid of this tap on the burette, I begin to turn it open while the acid drips slowly into my base, and the color will change from yellow to orange when there's neutralization. Once I get an orange color, I stop. What I have under here is a white tab. This white tab enables me to easily notice when neutralization or when there's a color change, so I can know when to stop at neutralization when neutralization happens. Let's imagine that neutralization happens and the volume of the acid in the burette has gone from 0 to this point. What I'm going to do now is I stop it. I stop the burette using the tap. I'm going to record these values now as my rough. Initial volume of acid was 0. Final volume of acid is 10. So I'm going to come here and write 0 initial 0.00, final 10.00. I move on. I take out this container. I repeat a new experiment. The whole thing I've done, I repeat again for a new one. But I continue with this volume of the acid. It was initially at 10. Doing a new experiment reduces the volume again down to 20 on the tube. So it means 10 for the first titer will be the initial, 10.00. The final, I got 20, let's say 22. So final will be 22.00. I continue like that. Let's say for the second one or the third one practically, I start from 22.00. Let's say I get something like 31.50. I fill up the burette again with the new acid or with the acids starting from 0.00, and I get 10.20 as the final. I fill up, I do my experiment for all, as many as I want or as accurate as I want it to be. That's the essence of having more than one titer. You want it to be as accurate as you can get. Next is to do its subtraction. 10.0 minus 0.0 give me 10.00. 22.00 minus 10.00 give me 12.00. 31.50 minus 22.00 give me 9.50. These are just values I'm just putting, okay? I'm just adding values. So they may not be consistent for the understanding. Then 10.20 minus 0 will be 10.20. Now, the volume you get by averaging these ones that are not the rough is going to be the volume of acid used. So here I'm going to have 12.00 plus 9.50 plus 10.20 all upon the average 3. So if I do the maths, Give me a minute to do the math. 12 plus 9.5 plus 10.2 all divided by 3. Give me 10.57. 10.57 cm cube becomes the volume of my acid that I use, or the average volume of the acid that I used in my titration. So going back to the formula now, I have now found the volume of acid that I used in my titration. What about the volume of the base? The volume of the base is the volume of these pipettes. So I also know the volume of my base as the volume of the pipette, because it is that quantity of base that you used, or that volume of base that you use. A question can give you the concentration of the acid or the concentration of the base. Any of them can be given to you. But the problem now is, how do we find this ratio Na over Nb? To find the Na over Nb is just to look at the mole ratio in the equation between the acid and the base. You look at the mole ratio in the equation between the acid and the base. What do I mean by the mole ratio? Let's take, for example, hydrochloric acid was the acid used. It now reacts with sodium hydroxide, and this forms sodium chloride and water. This is a balanced equation, I want to believe. There's one hydrogen, two hydrogen on the left, two hydrogen on the right, one chlorine on the left, one chlorine on the right, sodium 1, oxygen 1, oxygen 1. It is balanced. Now, I'm going to look at the coefficient. This gives you the mole ratio, the coefficient. The coefficient here is 1, here is 1, here is 1, and here is 1. It means the mole ratio will be 1 mole is to 1 mole. So this is the acid and this is the base. So Na will be 1, Nb will be 1. So by so doing, we can get Na and Nb. So it depends on which part or what part of the equation you're asking to get, or they're asking to get. You just make that part the subject of the formula. If we have a reaction like, say, not hydrochloric acid, let's say we have sulfuric acid reacting like this, sulfuric acid reacting with sodium hydroxide. This reaction gives sodium sulfate and water. Now let's see the balanced equation. Hydrogen is 2 and then 1 here, making 3, but it's just 2 here. Hold on. Sulfur is 1 here, sulfur is 1 here. Good for sulfur, not good for hydrogen. Oxygen is 4 plus 1, 5. Oxygen is 4 plus 1, 5. Good for oxygen. Sodium is 1 here, but sodium is 2 here. So what do? We put a 2 here for sodium. This has changed a lot of things. We go over it again. I shouldn't be teaching balancing chemical equations now. So we have 2 hydrogen here plus 2 hydrogen here makes 4, but just 2 here. So we'll put 2 here to balance it. So we have 4 hydrogen, 2 plus 2, 4 hydrogen here, 2 times 2, 4 hydrogen here. Hydrogen is okay. Sulfur is 1, sulfur is 1, sulfur is fine. Oxygen is 4 plus 2, 6. Oxygen is 4 plus 2, 6. Oxygen is fine. Sodium is 2. Sodium is 2. Everything is balanced now. Now the mole ratio here, looking at the coefficients, will be different in this reaction. This will be 1 mole is to 2. So Na in this case will be 1, and Nb, which is number of moles of the base, in terms of ratio, will be 2. So in that case, Na over Nb will be what? 1 over 2 in that case. So it depends on how it's applied, and more of those will come in our class in chemical stoichiometry when we're looking at stoichiometry. The next thing I want us to look at here is indicators that we use in titration. You already remember, I told you that we use indicators or indicators in a bottle. What are indicators? Indicators are substances that change their color when pH changes. They're usually made from flower petals, They change color with response or in response to changes in pH. Common indicators we have in chemistry, we have litmus paper, which can be red or blue. You have methyl orange, phenolphthalein, thymophthalate, and universal indicator solution or paper. I want to see their responses in neutral solution, in acid solution, or in basic solution. A red litmus paper obviously will remain red in acid or in neutral, but in acid it will remain red, while in base it will turn. Let me look at this again. A red litmus paper will turn to blue in base. Yes, in a basic solution it will turn blue. A blue litmus paper remains neutral blue. In an acid, it will turn to red, and in a base, it will remain blue. Methyl orange is orange in neutral solution, red in acid solution, yellow in basic solution. Phenolphthalein and thymophthalate, all these alane group, are colorless in both neutral and acid, but phenolphthalein is purple in base and thymophthalate is blue in base. The universal indicator is green in neutral, red in an acid, blue in base. It very much looks like what you have in the colors of a rainbow. And universal indicator is a very important indicator because it not only tells you if a medium is acidic or basic, it tells you the degree of acidity or basicity it has. So you remember what we done before in elementary school about pH being a measure of the degree of acidity or basicity of a substance. The pH indicator goes from 0 to 14, with 7 being neutral, and 0 to 6 being acidic, and 8 to 14 being basic. Very acidic solutions or materials will have low pH, like 1 and 2, and weak acidic materials will have high acidic values for like 4 to 6. Basic materials, weak bases will be like 8 and 9, and strong bases will have pH of about 13 and 14. Now, when an acid is strongly acidic, the universal indicator would be red in color. It shows the red color for strong acid, orange and yellow color for weak acids. Those ones correspond to the 4s and 5 and 6. In neutral, it's green. In weak bases, it's blue. In strong bases, it's blue too, but it tends to become purple and violet, as the case may be. Just very much like the ultraviolet, electromagnetic spectrum of light. So that being said, move to the next item. Okay, so the next item is qualitative analysis or SALT test. Salts, or the samples you'll be giving in your exams, would always contain two parts: the positive part and the negative part. There's going to be either a metal part and a non-metal part, or a metal or a cation and an anion part. Let me give you examples of these salts: sodium chloride, magnesium nitrate, aluminum fluoride, copper sulfate, calcium carbonate, ammonium chloride. Others that are not exactly salts: iron 3 oxide, zinc oxide, aluminum oxide. You'll notice that there's always a cation part in red and an anion part in green. Example, look here. In sodium chloride, for example, the sodium part is the anion part, the chlorine part is the cation. Magnesium ion plus 2, nitrate ion NO3 minus 1. Like that. Ammonium ion NH4 plus, chloride ion Cl minus. Ion 3 ion Fe plus 3, oxide ion O minus 2. Just like that. Aluminium ion Al plus 3, oxide ion O minus 2, and so on and so forth. Copper 2 ion Cu plus 2, sulfate ion SO4 minus 2. Now, we're going to have tests for the cations, which are the positive parts, and of course, tests for the anions, which are the negative parts. We're going to start primarily with the test for cations. There are two ways to test for cations. We have the flame test and the chemical test. Flame test for cations is often used when the chemical test will give you the same or almost the same result. For example, the group 1 and group 2 metals, their chemical tests give you the same results. Their chemical tests will always make what we call a white precipitate. So the best way to differentiate them is using a flame. Let's look at the flame test. How do you carry out a flame test? First of all, you dip a piece of nichrome wire. Nichrome wire is an alloy that contains nickel and chromium. You dip it in concentrated acid. After dipping it in concentrated acid, you hold it over a Bunsen flame, and the essence of doing that is to purify the nichrome wire. Why would you purify the nichrome wire? Sometimes in a laboratory or due to storage, dust particles may settle on the nichrome wire, and it may begin to give you wrong observations when you carry out the flame test. Incorrect observations. The dust particles themselves, they are chemicals. So you purify it. Next, you now dip the same wire into the acid again, but this time around, you're not purifying it, but you're trying to moisten it so that when you now dip the moistened wire into a powder of the metal powder will stick to the wire because it's been moistened. Now you now hold the wire over the transparent part of a Bunsen flame like this, and you observe the color change. If you're not going to use the nichrome wire, you can use a popsicle stick. Usually we use a popsicle stick when you have a solution that contains the cation. This case, we have a powder of the metal, but here we have a solution that contains the metal as a cation in it. For example, the first one with this can be used to get powder of zinc, but in this case, when you have zinc nitrate, for example, in solution, you would use a popsicle stick. And the popsicle stick, you first of all use a sandpaper to clean it. It's very important. When you're cleaning metals or cleaning solids in the laboratory, we use a sandpaper to purify it too. Now you dip the clean popsicle stick in the solution containing the metal like zinc nitrate aqueous solution, and then just hold it over the transparent part of the flame, and then you observe the color of the flame. So whether you're using a solution or using the powder, you hold over the transparent part of the flame, and with your eyes, you monitor the color of the flame. The flame color for lithium, if there's a lithium ion present, is red. Sodium ion will give you a yellow color because sodium burns with a yellow light. Potassium will burn with a lilac color, purple color. Calcium is brick red or orange or rusty red color. Barium is apple green or just green color, while copper is a bluish green color of flame. How do you carry out a chemical test for cations? Remember, we are still looking at the cations. No wonder everything I'm doing now is in red caption. So we're looking at chemical tests for cations. If you're carrying out a chemical test for cations, there are two substances that are usually used or that we usually make use of. They are aqueous solution of sodium hydroxide and aqueous ammonia solution. It's important. So in your alternative to practical, whenever you hear sodium hydroxide aqueous solution or ammonia aqueous solution, your mind should go to positive ion test or cation test. You put a small quantity of the sample you want to test, let's say salt or whatever sample it is, in a test tube, using a spatula. Then you add some water to the sample. In qualitative analysis, it's always a small quantity we use because we are not measuring quantity, we're looking at chemical behavior, so you don't need to waste. Just use small quantity, you get the result. Add some water to the sample in the test tube and stir to make a solution of the salt. Divide the solution into different test tubes as many times you want to carry out different tests as you wish. Now to one test tube, you add drops of aqueous solution of sodium hydroxide in drops, and then you observe what happens. Then after that, you now add sodium hydroxide solution not in drops this time, but in excess. You do the same thing for ammonia in drops and in excess. So it means, first of all, you have that solution of the salt. You want to add drops of sodium hydroxide aqueous solution. You observe what happens. And then you now add sodium hydroxide in excess. You observe what happens and you record. You do the same thing for ammonia in drops. You add, you observe what happens. And then you do the same thing in excess. You observe what happens. Let's see. The first ion we test for the IGCSE exam is the ammonium ion, the first cation. There are other cations. We have test for the ammonium ion, test for the copper 2 ion, test for the iron 2 ion, test for the iron 3 ion, and test for the alzica ion, aluminum ion, zinc ion, and calcium ion. Let's go back to test for the ammonium ion. To the sample you have prepared by this method I just described here, small quantity added in a test tube, add water, make a solution. To that solution now, add drops of sodium hydroxide using a dropper and you heat it up. So when you have, this is a solution of the salt or the sample you have, just add drops of sodium hydroxide. Just add drops of sodium hydroxide and then heat it up. Something will be observed. If this sample contains the ammonium ion, something will be observed. There will be effervescence. A gas will come out of that reaction. And if the gas turns damp red litmus paper to blue, that confirms that the salt or the sample is an ammonium salt. It contains the ammonium ion. Take, for example, if you are presented with ammonium chloride, for example, and you did not even know it was ammonium chloride. You take a small sample of ammonium chloride, put it in your test tube, add some water, make a solution, add sodium hydroxide, heat it up, there will be effervescence of ammonia. That gas is ammonia as a gas. And ammonia, like we saw before when we looked at tests for gases, turns damp red litmus paper to blue. So that is the positive test for the ammonium ion. It liberates, this is the ammonium ion in here, it liberates ammonia. And the simple reason for that reaction is because sodium hydroxide is a strong base. Like every strong base, they remove or displace weak bases, which is ammonia, from their compound. So this will give you ammonia plus sodium chloride plus water. This is the equation for the reaction. Please permit me to write it again. It's actually one very important equation. Should you be asked to write the equation, that's exactly what you would write. Sodium hydroxide reacts with the ammonium compound, okay, let's say ammonium chloride, to form ammonia as a gas, sodium chloride and water. But if they ask for the ionic equation, I hope this equation is correct. 1 sodium, 1 oxygen, 1 oxygen, 2 hydrogen, 1 plus 4 hydrogen, 5 hydrogen, 3, 4, 5 hydrogen, 1 chlorine, 1 chlorine is correct. Now, but if they ask for ionic equation, you just take the ammonium ion reacts with the hydroxide ion in sodium hydroxide, and it forms ammonia and water. This is the ionic equation. This is the ionic equation. Should the exam question ask you to write the ionic equation, this is the ionic equation for that reaction. So the formation of ammonia gas confirms that it contains or the sample contains the ammonium ion. So you have identified the positive parts of that salt. What about the copper 2 ion? You do the same thing. You add in sodium hydroxide to that sample. Drops of sodium hydroxide, excess sodium hydroxide, you add it to it. Drops of ammonia, excess ammonia. Now let's see what happens. For the copper 2 ion, when you add drops of sodium hydroxide, what will be observed will be a light blue precipitate. And when you add excess of sodium hydroxide aqueous solution, the precipitate would not dissolve, it will remain there. The essence of chemical tests is to observe insoluble precipitates formed. Insoluble precipitates come with various colors, and the color can tell you what ions are present in the sample. So chemical tests aim at observing the color of precipitate made. That is the essence of a chemical test. We are observing the color of precipitates made, and the color of those precipitates tell us what kind of ions are present in the sample. I don't know where to drop that, but that will do. I also put it in a square, so you take it as a note. Chemical tests aim at what? Observing the color, because many times these hydroxides meeting with the metal cation or the positive ion will form a precipitate, and the color of the precipitate is what tells us what kind of ion is present in the sample. Now let's look at, for the case of ammonia, when you add drops of ammonia to the sample, you also get a light blue precipitate. But when you add excess of ammonia, something now happens. It will give you it will turn into a dark solution. So I'm going to write here, in sodium hydroxide drops, we have a pale blue precipitate. Allow me to use PPT. And in excess, the precipitate does not dissolve. Allow me to do that for the first one. So when this happens, it confirms that what? That your sample contains the copper 2 ion. If you add ammonia, the same thing. In ammonia, you get a pale blue precipitate. Allow me to use PPT for precipitate. And in excess, precipitate dissolves into deep blue solution dissolves into a deep blue solution. Permit me to write this also here. Yes. Now, if you're asked to write the equation for that reaction, there's nothing. Just take the metal ion. Anytime you're asked to write the equation for reaction, take the cation, add it to the hydroxide ion, form the precipitate. Let's go. What's the metal ion here? Copper 2 ion added to what? To the hydroxide ion. This is the ionic equation. It gives me what? Copper hydroxide. State of matter. Ions are aqueous. Ions are aqueous. Precipitate is solid. So this is how you test, or the confirmatory test for the copper 2 ion. So if you have a solution and you carry out this test and get this result, it means copper 2 ion is present in the sample. We'll move to the next ion, ion 2 ion. For ion 2 ion, we are adding drops of sodium hydroxide, excess of sodium hydroxide, the same thing with ammonia. For ion 2 ion, you're going to get a green, I prefer to type, a green gel precipitate. And I don't want to type, let me just write it. You get a gel green precipitate. In excess, the precipitate does not dissolve. So here, in ammonia, you get exactly the same result, gel green precipitate, and in excess, the precipitate does not dissolve. If this happens, some people call it a dirty green precipitate. If this happens in your test, in drops, dirty green precipitate that does not dissolve, in excess, dirty green precipitate that does not dissolve. If this response is what you get for that solution or that sample, then it confirms that the sample has what we call the ion 2 ion. Now, if you write in equation, ionic equation for that reaction, I told you ion plus hydroxide ion will give us the solid. This is aqueous, this is aqueous, this is solid. We go to test for ion 3 ion. Something different happens if this ion is exhibiting the +3 oxidation state. When you add sodium hydroxide, it won't give you a gel green precipitate. Instead, it will give you a reddish brown precipitate, and the precipitate does not dissolve in excess sodium hydroxide. Same thing here. In ammonia, you get the same result. Reddish brown precipitate that does not dissolve. Reddish brown precipitate that does not dissolve in excess ammonia. All right. Now, it means if you get this kind of response, let me use this as reddish brown, for drops of ammonia and drops of sodium hydroxide, excess sodium hydroxide, ammonia, excess. If you get that result for that sample, it shows that that sample contains the ion 3 ion. That is a confirmatory test that contains the ion 3 ion. And next up now is test for aluminum ion. These ones, I'm not going to go into the details because they're basically the same steps you have to carry out. I have summarized it in a box like this. We have aluminium alzica. Now in this, first of all, what I did was I had a box. I divided into 3 columns and 3 rows. I wrote my aluminium ion, zinc ion, and calcium ion, the alzica. And then these remaining columns I further divided into 2 like this. And here I spelled white, W-H-I-T-E, and here nothing. Then I go D, 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 and here again nothing. That's basically what I did. Now, everything you have here is representing drops. Everything here represents adding your reagent in drops. Remember reagents I'm talking about sodium hydroxide or ammonia. Then everything I have here is representing the reagents added in excess. So this this column represents drops, this column excess. So the columns are representing drop and excess. While the rows, first row, sodium hydroxide, second row, ammonia. Sodium hydroxide, ammonia. Sodium hydroxide, ammonia. So what this means is this. The W here, that box means when I add drop of sodium hydroxide to a sample that contains the aluminium ion, a white precipitate is formed. This second box says, when I add sodium hydroxide to a sample that contains the aluminium ion, the precipitate formed dissolves. Now the next one below says, if I add ammonia in drops to a sample that contains the aluminium ion, a white precipitate is formed. This part explains that if I add excess of sodium hydroxide, excess of ammonia, the precipitate does not dissolve. Let me go one more time over the next one. Drops of sodium hydroxide to a sample that contains the zinc ion will form a white precipitate. In excess sodium hydroxide, the precipitate will dissolve. Drops of ammonia to a sample that contains the zinc ion, a white precipitate is formed. In excess of ammonia, the precipitate will dissolve. Here, if I add drops of sodium hydroxide to a sample that contains the calcium ion, a white precipitate is formed. If I add excess of sodium hydroxide, the precipitate does not dissolve. And here, if I add drops of ammonia to a sample that contains the calcium ion, there will be nothing, no change. If I add the ammonia in excess, nothing still happens. So my question to you is this. Ask yourself, can you explain this one? This one means if you add ammonia in excess to a sample that contains the zinc ion, a white precipitate is formed and that precipitate dissolves in excess ammonia. That brings us to the end of chemical tests for cations. Now let's look at chemical tests for anions now. But before we look at chemical tests for anions, something just came to my mind. Now, if we are writing ionic equation for, let's say, for the case of zinc, where it forms a precipitate, what do we write? The zinc, I prefer to write in white. The zinc cation with the hydroxide ion will form zinc hydroxide. This is aqueous. This is aqueous. This is solid. For the aluminium ion, Aluminium ion reacts with hydroxide ion to form aluminium hydroxide. This is aqueous, this is aqueous, and this is solid. So that holds true for all of them. Now let's come back to chemical tests for anions. Now, when we're talking anions, I'm talking about, I'm trying to go back. When we're talking anions, I'm talking about these other parts of your sample, the negative ion part of your sample. Anions. What happens in the case of anions? I'm going to briefly just summarize the test for anions and let you rest. Husband says no case after beating annoying housewife. I'm sorry I said that. I can't believe I said that, but it's fine. Husband says no case after beating annoying housewife. You see, each one of them is forward. This column forward, this column forwards. Now, husband here, I'm representing halide ions. Says here is representing sulfate ions. No here is representing nitrate ions. Case here is representing carbonate ions. After, here I am looking at the first letters now, A, B, A, and H. After, here, A is representing silver chloride. A, G is a symbol for silver, silver chloride. B here is representing barium sulfate. A here is representing aluminum pieces. And housewife H representing hydrochloric acid or any acid at that. Now, when you are having a test or carrying out a test for anions, this is a summary. It's just for you to prepare for your exams and to know the key points. Ordinarily, you carry out this reaction. These are things you have to note about the reactions, about these tests. They would normally, or the test would usually involve adding things like, for the first one, testing for halide ions, to the sample, you add nitric acid. Then you're going to add the question will always say the added nitric acid, then followed by silver nitrate. Once you hear silver nitrate, know already that hey, silver nitrate or silver chloride, they're talking about halide ions. Halide ions. Now, what you will observe, if the anion is a fluoride ion, is that there will be no precipitate. If the anion is a chloride ion, there will be a white precipitate. If the anion is a bromide ion, there will be cream precipitate. If it's the iodide ion, it is going to be a yellow precipitate. Observe that the color of the precipitate, all these ions have negative charge. The color of the precipitate is getting darker as you go down. And how does this happen? Silver as an ion, the equation for the reaction, would react with, this is wrong, with the chloride ion. Since it's ionic equation, reacts with the chloride ion, which is also aqueous, to form silver chloride as a solid. For the bromide ion, the equation for the reaction is silver ion reacts with the bromide ion to form silver bromide. For the iodide ion, silver ion reacts with the iodide ion to form silver iodide. And all of these ions are aqueous. All of these ions are aqueous. But these precipitates that are white, cream, and yellow are solids. It's important. Now, for the sulfate ion, we move to the sulfate ion, which is the next. The same thing will happen. You hear, or in the test, they will add nitric acid, then followed by aqueous barium sulfate. So where you hear the word barium sulfate, your mind goes to beaten, that means they are testing for the sulfate ion. A white precipitate will be the result. The positive result will be a white precipitate. Otherwise, it's not the barium ion. Otherwise, it's not the sulfate ion you're testing for. A white precipitate will be formed how? The barium ion reacts with the sulfate ion to form barium sulfate as a solid. This is aqueous. This is aqueous. Ions are aqueous, and the precipitate is a solid, and it is a white precipitate. Next up, we go to the nitrate ion. For the nitrate ion, you will not hear anything like adding nitric acid. You would add sodium hydroxide aqueous, then aluminum pieces of aluminum will be put in that reaction. But where you would pay attention is the aluminum pieces. Once you hear aluminum pieces, you think of annoying, and that means you are testing for the nitrate ion. And what is the result for that test? Ammonia gas will be made. Ammonia gas will be made. And of course, it follows the same reaction that what we saw in the first case, where ammonia gas is produced when sodium hydroxide reacts with a material that contains the ammonium ion. So in this case, ammonia gas will be made, and the gas turns damp red litmus paper to blue. That is what? Ammonia, because it is a basic gas, like we said before. It turns damp red litmus paper to blue. Now we move on to the carbonate ion. In the carbonate ion, any acid will be added. It may be nitric acid, maybe hydrochloric acid, maybe sulfuric acid. So long as it's an acid, there's always H in an acid. Now remember that acids react with carbonates to form carbon dioxide. That is why the result will give you an effervescence. Because of carbon dioxide, the result will give you an effervescence. Positive result, effervescence will be observed. Once you have a sample and you observe effervescence, after adding any acid, it tells you that what? The salt must contain the carbonate ion. So to further explain this is a tube I have, and this tube has my solution. What I just need to do is to add those substances. If I add HNO3 and then I add silver nitrate, think of the halide ions. So if you get those colors white, or you don't get white, you get cream, precipitate, you don't get cream or you get yellow, that tells you that what? It is the halide ion, and you were able to point which halide ion has its presence in this sample. Now, what about if I don't add this and I add nitric acid and then followed by something like barium nitrate? Barium nitrate. If I add barium nitrate, I get a white precipitate. That tells me that this must contain the sulfate ion. Now, what if I have a situation where I'm not adding nitric acid, but the question talks about adding sodium hydroxide followed by aluminum pieces? Then this sample and must be the nitrate, it must contain the nitrate ion, because if there's an effervescence, ammonia is made, and this ammonia turns red litmus paper that is damp to blue color. And lastly, if I have a situation where I add any acid at that, and I am seeing effervescence or bubbles, that tells me that that must be carbon dioxide, and this sample must contain the carbonate ion. In our next session, we'll be looking at how to solve alternative to practical questions practically. So far, we have actually addressed all of these, talking about collecting gases, separating techniques, volumetric analysis, and salt analysis. Thank you for your time.